Jupiter is not the planet you think it is. Almost everything we learned about it in school was a rough first draft based on blurry images and clever guesses rather than hard data. Today, thanks to deep space missions from NASA and ESA, we know that Jupiter is not just a simple ball of gas. It is a layered, dynamic world where matter itself is crushed into exotic new forms, and its true nature is still challenging our best physics. First close-ups of a giant. The first time humanity truly saw Jupiter up close was in the 1970s, when NASA's Pioneer 10 and Pioneer 11 spacecraft raced past the giant planet and sent home grainy but unforgettable photos. A few years later, Voyager 1 and Voyager 2 transformed those still images into time-lapse movies, revealing belts, storms, and a great red spot swirling like a wound on a planetary scale. These flybys were spectacular, but they were also frustrating. They showed us Jupiter's turbulent face without telling us what was hiding underneath, or how such a monster of a planet could have formed in the first place. Just how big is Jupiter? Jupiter's size is hard to grasp with human intuition. By mass, it is more than twice as heavy as all the other planets in the solar system combined, and its volume is large enough to swallow about 1,000 Earths. If Earth were the size of a grape in your hand, Jupiter beside it would be a full-size basketball filling your field of view. That immense bulk means an equally immense gravitational pull, powerful enough to reshape its own interior and to fling or capture comets and asteroids that stray too close. Two competing origin stories. For decades, scientists argued over two main stories for how a world like Jupiter could be built. In the first, a rocky, icy core several times the mass of Earth grows inside the young solar system's disk of gas and dust. Once it becomes large enough, its gravity sucks in huge amounts of surrounding hydrogen and helium, ballooning into a gas giant. In the second, Jupiter begins more like a failed star. A separate clump of gas collapses under its own weight, too small to ignite nuclear fusion, but large enough to form a brown world that later falls into orbit around the Sun. If the first story were right, we would expect a solid, compact core buried beneath layers of gas. If the second were right, Jupiter might have no clear core at all, just a smoothly changing interior. A cosmic accident. Shoemaker Levi 9. A breakthrough came not from theory, but from a cosmic accident. In July 1994, fragments of comet Shoemaker Levi 9, previously torn apart by Jupiter's gravity, plunged into the planet's atmosphere at about 60 kilometers per second, over 200,000 kilometers per hour. Each fragment exploded with the energy of millions of megatons of TNT, more than all nuclear arsenals on Earth combined, carving dark scars into Jupiter's southern hemisphere that grew larger than the Earth itself and lingered for months. For the first time, astronomers could watch in real time what happens when material from deep below Jupiter's cloud tops is blasted upward into view. Galileo flies through the debris. By extraordinary timing, NASA's Galileo spacecraft was already on its way to Jupiter and had a front-row seat as the comet hit. When Galileo later arrived in orbit, it flew through the aftermath of those impacts and dropped a probe directly into Jupiter's clouds. The probe plunged for about 58 minutes, measuring temperature, pressure, winds, and chemistry before it was destroyed by heat and pressure greater than any found on Earth. Among its surprising findings was an unexpectedly dry atmosphere in the entry region and evidence that water and other heavy elements are mixed deep within Jupiter, hinting that the planet's interior is far more complex than a simple ball of hydrogen. Enter Juno, peeling back the clouds. To truly probe beneath the clouds, NASA launched the Juno spacecraft in 2011. Juno arrived at Jupiter in 2016 and began a series of close polar orbits skimming just a few thousand kilometers above the cloud tops while mapping the planet's gravity and magnetic fields with exquisite precision. Those subtle tugs and twists in the gravity field let scientists weigh different layers inside Jupiter, turning the whole planet into a natural CT scan. What Juno revealed shocked planetary scientists. Jupiter does have a core, but it is not the dense, compact iron rock ball we expected. A fuzzy, diluted heart. Instead of a neat central kernel, Juno's data point to a fuzzy core, a huge region in which heavy elements are diluted and mixed with hydrogen and helium over almost half the planet's radius. In this inner zone, there is no sharp dividing line where rock ends and fluid begins. Instead, composition and density change gradually, like layers of soup stirred together. One leading idea is that Jupiter may have once had a solid core, but a colossal collision with a massive protoplanet billions of years ago shattered and mixed that core with the surrounding hydrogen. Computer simulations support the idea that such an impact could create a diluted core, although they also show that the structure might slowly reconcentrate over time, raising new questions about why Jupiter's heart is still so fuzzy today. From clouds to a supercritical fluid. To understand why Jupiter is more than just gas, we have to dive downward. The striped cloud tops that we see from space, made largely of ammonia ice and other trace chemicals, are relatively thin, averaging only tens of kilometers deep. Below them, temperatures and pressures climb rapidly. Hydrogen and helium no longer behave like ordinary gases or liquids. At depths where the pressure is tens to hundreds of thousands of times Earth's surface pressure and temperatures are thousands of degrees, hydrogen becomes a supercritical fluid, neither a traditional gas nor a normal liquid, but a dense, churning phase with properties of both. There is no solid surface to stand on, just a gradual thickening fog of hydrogen turning into an enormous global ocean. Lightning and storms in the upper layers. Near the top of this ocean, water and ammonia play an electrifying role. Juno and earlier missions have detected lightning flashes on Jupiter that can be up to 3 times more energetic than the biggest lightning bolts on Earth. Models based on these observations suggest that water ice, liquid droplets, and ammonia act together like natural antifreeze, allowing mushballs, slushy hailstones made of water and ammonia, to form and fall deep into the atmosphere. As they fall, they carry heavy elements downward. As they later evaporate and rise, they help drive enormous storms. Features like the Great Red Spot are not just cloud patterns on the surface. Juno's microwave and gravity measurements show that this gigantic storm system extends hundreds of kilometers down into Jupiter's atmosphere. It is like a hurricane, so tall that if it were placed on Earth, it would reach far above the altitude of the International Space Station. The Great Red Spot's true depth and color. The Great Red Spot itself is wider than the Earth and at least 300 kilometers deep, rooted well below the visible cloud tops. Its rusty color likely comes from sunlight breaking apart simple molecules high in the atmosphere, creating more complex compounds, chromophores, that tint the storm red when mixed with ammonia and other gases. Because it towers above the surrounding clouds, it soaks up extra ultraviolet light from the sun, which helps drive those chemical reactions. Imagine a storm system taller than 10 stacked Everests and wide enough to swallow our planet whole, persisting for centuries in an atmosphere lit by constant lightning and bathed in radiation from Jupiter's intense magnetic field. The largest ocean in the solar system. Deeper still, at pressures millions of times higher than Earth's surface, hydrogen behaves in ways we can barely reproduce in laboratories. Somewhere tens of thousands of kilometers below the clouds, hydrogen transitions into a form often called liquid metallic hydrogen, a dense, electrically conducting fluid where electrons are free to move, more like the behavior of metal than of a typical gas. NASA models that Jupiter's outer envelope is molecular hydrogen, but beneath that lies a vast layer of metallic hydrogen, potentially tens of thousands of kilometers thick. This layer is, in effect, the largest ocean in the solar system, an ocean not of water, but of compressed hydrogen under temperatures that may reach 10,000 to 20,000 Kelvin. A planetary-scale dynamo. Because metallic hydrogen can conduct electricity, Jupiter's rapid rotation, once every 10 hours, turns this deep layer into a colossal dynamo. As the fluid metallic hydrogen circulates, it generates powerful electric currents, which in turn create one of the strongest magnetic fields of any planet we know. That field traps charged particles, forming intense radiation belts that can fry unprotected electronics and even damage spacecraft. Juno follows a highly elongated orbit and dives in only briefly each pass to avoid the worst of that radiation. The result is a planet wrapped in invisible magnetic power, with auroras at its poles so energetic that they outperform Earth's northern lights many times over. The mystery of the core. At the very center of all this lies Jupiter's enigmatic core region. Earlier models assumed a neat Earth-sized sphere of rock and metal. Juno's gravity data, however, fit better with a diffuse mixture where heavy elements blend into metallic hydrogen across a broad zone. That fuzzy core extends perhaps half the way out from the center, more like a thick stew than a solid ball. Did a massive collision early in Jupiter's history stir its interior? Did heavy elements slowly dissolve into hydrogen over billions of years? Computer simulations suggest that giant impacts can create a diluted core, but they also hint that over time, the core should reconcentrate. So the fact that Jupiter's is still fuzzy means something unusual happened or is still happening deep inside. Why Jupiter matters for everything else. Understanding Jupiter is not just about one weird planet. It is about rewriting our story of how planetary systems form. Gas giants like Jupiter are common around other stars, and their size and position can control whether smaller, rocky worlds like Earth can even exist. By mapping Jupiter's interior and atmosphere, missions like Juno help scientists test models of planet formation, from the original solar nebula to violent collisions and long-term mixing. The same physics that squeezes hydrogen into a metallic ocean on Jupiter likely operates in many hot Jupiters and giant exoplanets we see orbiting distant stars, meaning that this one nearby world is a laboratory for the entire galaxy, a living mystery in our sky. So yes, Jupiter is wrapped in clouds of gas, but it is not just a fluffy gas ball. Beneath those bands and storms lies a supercritical ocean of hydrogen, a planet-sized shell of metallic fluid, and a fuzzy, partially dissolved core that may be the scar of an ancient collision. It is a world where lightning rips through ammonia water clouds, where chemistry and gravity forge new states of matter, and where our best theories are still being tested with every new orbit of Juno. Jupiter hangs in our night sky as a bright star, but up close, it is a colossal natural experiment, daring us to understand how planets, atmospheres, and even stars themselves come to be. If you want to keep diving into hidden oceans, fuzzy cores, and the wild frontiers of real space science, make sure to subscribe and join us on the next journey through the cosmos.